Welcome to this explainer. Look, whether you're a PGY2 literally sweating through your very first retinoscopy or you're gearing up for your OCAPs, we know that true clinical mastery comes from understanding the why, not just memorizing the what. So today, we're going to build a flawless, bulletproof mental model of optical refraction. Today, we master the absolute essence of spectacle correction.
Let's kick things off with a classic board-style question, just to prime our minds and frame our entire discussion. I want you to think about every single prescription you've ever written in clinic. What is the single underlying optical secret that links every myopic spectacle, every hyperopic contact lens, and every refractive surgery? Take a second. What is the one physics equation we're trying to solve every single time we put glass in front of a patient's eye?
So here's our game plan for today. 1. The far point problem. 2. Myopia and hyperopia. 3. The golden rule. And 4. Correcting the eye. Let's get right into it.
All right, section 1, the far point problem. First things first, we really have to establish that refractive error isn't a disease in the traditional pathological sense, right? It's simply an anatomical mismatch. Let's start with the far point. By definition, this is the location in optical space that is conjugate with the retina when the eye is not accommodating. I want you to underline that phrase, not accommodating, in your brain right now. This is the eye's absolute resting state. The far point is the specific, physical location out in the real world where, if you place an object, the completely relaxed eye sees it in crystal clear focus.
Now, let's think about this concept of conjugate points. You can think of them as an unbreakable optical partnership. If the far point is point A out in space, the retina is its conjugate point B. If light originates at point A in space, it perfectly focuses at point B on the retina. And conversely, if we shine a light into the eye, like you do literally every day with your retinoscope, the light reflecting off the retina at point B will focus precisely back at point A. They are permanently, beautifully linked by the specific refractive power and axial length of that individual patient's eye.
Okay, time for a little active recall. This is an absolute classic OCAP pearl. If a normal, emmetropic eye sees 20/20 at distance without any correction at all, where exactly is its far point located in optical space? I want you to literally pause and answer this in your head before I give it away. Where is the object that this unaccommodated eye sees perfectly?
Did you get it? The emmetropic eye has its far point perfectly at optical infinity. When an emmetrope looks at a mountain in the distance, parallel rays of light, meaning light with zero vergence, enter their eye, and their natural anatomy perfectly converges those rays onto the fovea without a single diopter of accommodative effort. Infinity is conjugate with their retina. This right here is our ultimate clinical goal.
Moving right along, section 2, myopia and hyperopia.
Let's contrast what happens when the anatomy isn't quite perfect. Take a myopic far point. A -2 myope has an eye with too much plus power. Because of that, their far point is drawn into exactly half a meter anterior to the cornea. They see perfectly at that spot, but everything beyond it, totally blurry. Now contrast that with the hyperopic eye. This eye doesn't have enough plus power, or maybe it's just too short. Its far point is actually pushed completely through the eye, sitting in virtual space behind the globe. The only way this patient can see clearly without accommodating is if incoming light is magically pre-converged before it even hits their cornea.
Now watch out for this common board trap, because it's also a profound clinical challenge. Our goal is clear vision at optical infinity, where vergence is 0. But an amyotropic eye is only in focus at its far point. Without refractive surgery, there is absolutely no escaping this anatomical fact. The myope's eye demands that an object be 50 centimeters away. So how on earth do we take an eye that demands an object be half a meter away and allow it to see a star that's millions of miles away?
Which brings us to section 3, the golden rule.
Before I give you the golden rule, we need to define a property of the spectacle lens itself, and that's the secondary focal point. This is an intrinsic property of the physical glass you're holding in your hand, entirely separate from the eye. It's the exact, precise location where parallel rays of light coming from infinity will form an image after being bent by that lens. Think of holding a plus lens up to the sun to burn a hole in a leaf. That burning spot, that is the lens's secondary focal point.
All right, here's the secret. If you only write down one thing today, make it this: immutable law of optical physics. Place a lens in front of an eye so that the secondary focal point of the lens completely coincides with the far point of the eye. You are taking a property of the lens and physically overlapping it in space with a property of the eye.
When you do this, it's pure magic. Let me show you exactly why.
Let's put it all together in Section 4, Correcting the Eye. Let's actually walk through this chronological optical journey step by step. Imagine a myopic eye looking at infinity. Step 1. Parallel rays arrive from infinity. Step 2. Refraction. Those rays hit the minus spectacle lens you just prescribed, which diverges them. Step 3. An image forms. Those diverging rays now appear to originate from the lens's secondary focal point, forming a virtual image right there. Step 4. Alignment. Because you, the brilliant clinician, chose the correct lens power, that secondary focal point perfectly matches the patient's far point. And finally, Step 5. Sharp focus. You see, the eye has no idea the light originally came from a mountain, it just senses rays coming from its own far point and easily focuses them right onto the retina. You've essentially tricked the eye into seeing infinity by funneling it perfectly through the far point.
And it works the exact same way for our hyperopic patients. A plus lens takes parallel rays from infinity and adds convergence. It aims them precisely at its secondary focal point, which you have cleverly aligned with the hyperope's posterior far point. The hyperopic eye happily accepts these pre-converged rays and perfectly focuses them on the retina. It's the exact same optical law, just applied with converging vergence instead.
Before we completely wrap up this explainer, let's do a quick rapid-fire review of our top board pearls. 1. The unaccommodated far point is always conjugate with the retina. 2. Emmetropes have their far point at infinity, myopes anteriorly, and hyperopes posteriorly. 3. The golden rule is matching the lens's secondary focal point to the eye's far point. Now I want to leave you with a rather provocative clinical thought for your next rotation. We just proved exactly how we can perfectly correct distance vision. But think about this. If you perfectly align those points, altering the vergence of all incoming light, what happens to the optics of their near-reading vision? How does this new lens actually impact their accommodating eye compared to when they just take their glasses off? Sketch out that ray diagram tonight. Keep thinking critically, and I'll see you in clinic.